Okay, so I was talking about that the advantages with the Grubbs complexes is the functional group tolerance, and the disadvantage with this one is tri and tetra substituted olefins. They cannot undergo metathesis, which is the advantage in case of the shock carbon. So, but here we can realize the fun factor that both the shock as well as Grubbs catalyst, they are having a loop coordination number, so that easily when fortune is leaving, olefin can be attacked easily. So this is the one common factor they both are having in hand. So what we have seen in this particular, I'll just write here. One common factor between shock and Grubbs catalyst, they both they have a low coordination number, which arise from the dissociation of their phosphine group. Okay, just remove this. So we'll just take a recap of what we have seen in this one before starting the cross metathesis. So here we said that we have taken the Grubbs catalyst. We talked about this one. We see for solving mechanism. We also followed in terms of hysterics and electronics, and we did the Herman's comparison study. Then we talked about the alkene metathesis catalyst. And here we came to the conclusion that shock and Grubbs both are having their advantage and disadvantage. And now we will be covering the cross metathesis topics. So here just to recap, we started with olefin metathesis catalysis. So you can see how the two different olefins they combine together to give a new product. So it requires a metal carbon catalyst. After that, in metal carbon catalyst, we saw that ruthenium makes the best catalyst because it is easy to handle, easy to prepare, and they also have the functional tolerance. Moving ahead, if we'll talk about the ruthenium-based catalysts, we talked, they have been investigated and developed by Grubbs. So the Grubbs catalyst, the first generation is having the cyclohexyl phosphine groups, whereas it has been replaced by N-cyclic carbon kind of group in second generation with a different origination. Moving ahead, then we try to understand the kind of mechanism which comes from the Grubbs catalyst system. So here we know that it is having the PCY3 group over there. It will first dissociate. It will first dissociate because of the bulkiness which is surrounded the metal. If we will be having PPH3 and you are having PCY3, obviously PCY3 is more bulky in nature. So because of the sterics, it will dissociate the other group. Dissociation of the group makes it coordinatively unsaturated, and that creates a vacancy over here. When vacancy is being created, it can easily take up your olefin, and the interaction between metal and olefin is not that straightforward until and unless it is having an electron density around it, which can come from your group. If it is electronically rich group, it will give you more density, and that would help in back donation with the olefin. And once olefin binding and goes through metallocyclobutane kind of intermediate, which is being given by Chauvin, therefore, ultimately, it would lead to form your product, which we saw here. It will give you the product. Moving ahead, what are the different ways that we can increase the activity of our Grubbs catalyst? Was either to have the phosphine dissociation rate very faster. That means we can replace it by more bulky groups or having more cone angles. the more bulky groups are having more phone angle, then or we can replace the other groups by bulky groups. Like if we are having chloride groups attached to the metal, so we can replace it by iodide. If we have chlorine, bromine, iodine, so the iodine would be having more than bromine than chlorine. The activity will be here. So more electron donating phosphine groups, that means more electron density, and that could increase the olefin. So this is to increase the rate of your olefin binding. Moving ahead, then we saw that if we replace a PCY group with this NHC group, that is a drug second generation, then more activity has been seen. So how? So to understand that, we can see that when PCY3 group has been replaced by this NHC group, NHC group is a sterically bulky group. Also, it is giving more electron density to metal, makes a bond very stronger. Therefore, the pi interaction with the olefin becomes even more feasible and the activity is more. So, by replacing the PCY3 group in Grubb's first catalyst with NHC in second generation, more bulkiness, so the dissociation is faster, more electron donation, olefin binding is faster, so overall activity is increased. To see or to compare this one, Harman did a demonstration by comparing the activity of Grubb's first and second generation in ROMP, that is ring opening metathesis polymerization of the cyclooctane compound. And what he saw that if you will see the percentage yield is increased and then becomes constant when we are having the second generation catalyst compared to the Grubbs one, which steadily increases. Moving ahead, then we have alkene metathesis catalyst, where we have already explained the formation of tungsten based catalyst system. And here we can see the formation of W double bond CH2. Then we compare the shock complexes, which is having the CH3 electron withdrawing group, which is helping it to make the activity increased, and also it is possible to do the metathesis of here substituted olefins, even up to tri and tetra. But disadvantage is that they have poor functional group tolerance. And at last, we saw that Grubbs complexes, which is having more tolerance, function group tolerance, but they can't do the metathesis of substituted olefins. So, but both of them, they are having a common factor of low coordination number. Now we can so now we can have our another topic. So now we will be, so up till now, what we have covered. So we have talked about Grubbs and shock catalyst or the complexes. We have seen the comparison. Also, we have seen both first and second generation Grubbs catalyst. Second one is more suitable in having more activity. We have seen the advantages as well as disadvantages. with these complexes in case of metathesis reaction. We have also seen the Harman's demonstration by using the cyclooctane group in ROMP metathesis, which is ring opening metathesis polymerization. Now, our next topic of concern is the cross metathesis. If you are remembering what we have discussed in our last live session, maybe second live session, there was something called self metathesis and cross metathesis. The self metathesis is going to have, if we are having, so this would be a same kind of olefin. You're taking two molecules. So if I am removing the two from here, and if I am having the same molecule, so they both undergo the metathesis and they will end up giving us a new. So these two groups will combine one alkene and other will give you the CH2 CH2. So this was the self metathesis. Now we are talking about the cross metathesis. That means the groups could be different. So if I'm taking R1, R1 could be anything, and second I'm taking R2, where R1 is not equals to R2. In presence of the catalyst is nothing but your metal carbene, which we have been discussing for a very long time. And here the possible product could be your R2 and CH2, CH2. So this is the way, this could be one such thing, or even if we are having R1 with R2 and another type of alkene is R3 and R4. So in presence of the catalyst, it would be giving you R1 combining with R3, R2 combining with R4. It could be a possibility of R2 combining with R3 and R1 combining with R4. That is called as cross metathesis. So why it is important? Because cross metathesis has been seen with an advantage. It has not been discussed so much, but it has an advantage in case of shock, which is nothing but shell higher olefin polymer process. Don't get overwhelmed with the name of this particular thing. So I'll try to understand. So what happens is, like, the history of it says that there was a need to have detergent molecules, and those making the detergent we required long chain molecules, olefins basically. So it was seen that the origin. So we had a requirement for making soft detergents and not the hard detergents, which could easily dissolve in water and so on and so forth. Or this requires long chain linear olefins. So, or alcohols. So for making this kind of system, according to the distribution, it was seen that the carbon number and your mole percent over here. So the distribution was kind of this one. If we are having carbon number less than C12 and greater than C18, this is C18. So this region is actually which is required for this particular purpose of making a soft detergent. It's very hard to get it. So that is where the cross metathesis comes into picture, and how the shock kind of process is being devised. So we'll just give a flow diagram over here. So what are we trying to say? You will get to know by just understanding this flow diagram of shock process. So this is the shock production plant. So generally it starts with the ethylene only. We are starting with the ethylene, and then firstly it will go to the first chamber, which is the oligomerization chamber in presence of the catalyst. It will make an oligomer of the ethylene in presence of the nickel catalyst, and then in another chamber it would be having catalyst recycling. That means the catalyst, after making an oligomer of ethylene, it would recycle, and then the catalyst can be used for another turn. So it will regenerate the catalyst. Now, once it is done, then it will go to your distillation chamber to distill off whatever the required products at one step. So in the distillation chamber, what will happen? This will distill off the alpha olefins for market that we were talking about, which range from C12 to C18, that is required for the soft detergent. So after distillation, we can get it over here. And whatever the remaining fractions are there, the remaining fractions, which is less than C12 and greater than C18, they will then undergo, I'll just highlight with the green color. So then they will undergo to another chamber, which would be your isomerization. So here, the remaining fraction would get isomerization C12 and greater than C18. And these isomerizations thing will then go to the cross metathesis process. We will take up the example to make it more clear. So this cross metathesis is going to give you what kind of products? This will give you C11 to C14 fractions, which are required for hydroformylation and so on and so forth. And whatever is left, it goes again back to this isomerization. If C11 to C14 are there, what is being left? It is left as C10 and greater than C14. So whatever the fractions are being left, they will again being sent to the isomerization, and they will again go and make this C11 and C14. So this is the shop production plant where at one end we can produce the C12 to C18 carbon number of olefins, which can be used for making the soft detergents. And the other way, we can do the isomerization and can produce the fraction of the olefins, which can be used for the hydroformylation other processes. So this was the advantage of doing the cross metathesis, isomerization and oligomerization. So we can take up the example here. Take for example, if we are having, I'm talking about the isomerization. So isomerization will start with the less than C12 and greater than C18. So if I'm taking a moiety, which is this one, this is one octene having carbon number 8. 1, 2, 3, 4, 5, 6, 7, and 8. And after isomerization is just here is the position isomerization. So here we are having the position goes from 1, 2 to now 4, 5, and it is giving us this one. This is now 4 octane. So this is just a position isomer. So call it as A. And secondly, we are having another group which is more number, and that is your C20. It's 1 C20 is the number. Here it is, that means C greater than 80. This is C less than 12. That is the region that we were showing. Now it will undergo isomerization. And what it will form this kind of structure where here it is 8, here it is also 8, and in between it's 2. So that becomes 10 to same, just the double, the number has been changed. Now we call it as B. Once the isomerization is done, it will do the metathesis because we are having different kinds of alkene, as I already explained. So this was A plus this was B. As you can see, these two are two different olefins. So this is called as cross metathesis, which we just explained in the flow diagram. After the isomerization, the both parts will go under cross metathesis, and therefore they end up having this kind of product, which is having C10. And if you'll just count, this is C14, which is lying between C12 to C18, and this is being used for making soft detergents, and that therefore it fulfills the market requirement, and this is the process that we are looking for. I hope this is clear now. Again, example that we can take into picture is if we are starting with, say, I have this kind of an olefin, CH3 and CH3. This is C4 moiety that is less than C12 plus C10H21, C10H21, and if you count, this is C22 that is greater than C18. And now, if I am using a molybdenum oxide and aluminum oxide as a catalyst, this will give me, this is a cross metathesis again. Now the cross metathesis is going to give you CH, CH3, C10, H21. This is total C30 number that can be used for your soft detergent making because it is lying in that region. So what we have understood till now, how the shop process works, how the isomerization works, and then after isomerization, how the cross metathesis gives us the required C carbon number, which is required for making the soft detergents. But there are certain limitations with the cross metathesis that we will take up into picture. So the limitations, that is the last topic of the discussion. Then we can take up the assignment problems. Cross metathesis. So here, when we are seeing this kind of system, we don't know what kind of isomer it is being formed. It can be E isomer, it can be Z isomer, it can be homodimer, or so and so forth. So therefore, both the olefin isomers, which are dependent on the position of the groups, E and Z isomers, they are formed in the mixture of products. So also we will be having including of homodimers, branching, as well as EMZ combination. So if I'm starting with R1, this is the two different olefins. That's why we are calling it as a cross metathesis in presence of the catalyst. It will give you CH2 and CH2 group over here. C2H4 is out. Now what it can do, it can take R1. Here I don't know the direction. It can be like this one also, downside. It can be like Z isomer like this side. So the curvy nature shows you that we are not sure about the direction, and that's a mixture of products. Similarly, continuing with that, we can have similar case with, say, first we got to know that it can form this kind of E or Z mixture of the olefin, which is the major product. Also, the two molecules, they can go under a homodimerization. So homodimer, they will form with R1 itself. There also we don't know that direction. Here also we don't know the direction. So these are the homodimers. So this is your actual cross metathesis product. but this is your side product of homodimerization, where two molecules of the same olefin can combine together to give you a ENZ mixture. Here also we don't know, but here also we are having ENZ mixture. So this is the challenge that we have, or this is the limitation that we have with it. So here, how we can overcome this challenge? So we need to find out a way to increase the selectivity of cross metathesis reaction, leaving out the homodimerization. So what we can do, we can use a Grubb catalyst in that condition, as anyway we are using a catalyst, but Grubb's catalyst will increase the cross metathesis yield and decrease the homodimerization. Say for example, if I'm starting with this particular olefin, and now I have introduced the Grubb's catalyst. You have already know that what is a Grubb's catalyst. It is mainly of ruthenium, and the first generation Grubb's catalyst is having cyclohexyl phosphine kind of group with chloride groups and having carbene with a substitution of pH group. This is your first generation. Similarly, if you replace the PCY3 group with N-heterocyclic group, that becomes your second generation. We are not going into that detail. The main thing is like talking about the Grubb's catalyst. In presence of that, these two both will combine together to give you 1, 2, 3, 4. Okay, so here is your double bond. So this is your homodimer, because only one system is combined 2 times to give you a homodimer. Now, if I introduce the second olefin, so therefore we will be having now R2, R1. So this is your heterodimer. Most importantly, your cross metathesis product. So if you will go in this particular direction, firstly introducing your Grubb's catalyst, which will give you a homodimer, and then homodimer itself is connecting with another olefin to give you a final product. So that would reduce the concentration or the product yield of a homodimer, and you would only be having a cross metathesis product. So this was it for our today's live session, where we have discussed. I'll just repeat it one more time. So I'll show you what we have started. Those who have joined late, they can just see that now we have covered this cross metathesis, shock, and limitation. So these were the topics that have to be considered in today's live session. We talked about the Grubb's catalyst, their mechanism, influence of the sterics and electronics, Hallman's comparison, alkene metathesis catalyst, cross metathesis, shock, SHOP, and limitations of cross metathesis. So I'll repeat it one more time. We started with the olefin metathesis. Whenever we are talking about olefin metathesis, we generally consider the cross over here, where R1 and R2 are not equal, and they will give you a new olefin. Now here the metal carbene catalyst we have discussed in last lecture. The catalyst that we are terming over here, it is nothing but a metal carbene, and carbenes we have generally seen in Fischer and Stock. Fischer carbene is known as a singlet carbene because one electron stays in the sp2 hybrid orbital, and both the electron stays in the sp2 hybridized orbital. Whereas in case of Stock carbene, one electron will be staying in both sp2 hybrid orbital as well as the pc orbital, that you can go and check again. Then our main feature was like, what is the metal over here? So we have different kinds of metals: tungsten, rhenium, molybdenum, ruthenium. Mostly with the ruthenium-based systems, they are most active. That is covering the Grubb's catalyst. With molybdenum, it would be having a Stock one. What are the advantages with the ruthenium-based catalyst? Because they are easy to handle, they can be easily prepared, and most importantly, they are having a functional group tolerance. Moving ahead, we saw different types of Grubb's catalyst. So having a ruthenium metal, when we have a PCY3, that's a first generation catalyst. When this PCY3 is being replaced by this N-heterocyclic carbon, that becomes a second generation, and there are different versions of it. Moving ahead, earlier we saw the metathesis reaction mechanism using a Schrock carbon or a Fischer carbon. Now we are considering a Grubbs catalyst, and then we have to understand the metathesis reaction. So how it goes. So say for example, this is our metathesis catalyst where PCY3 is our group. Firstly, this will go away to make a vacancy. Once this vacancy has been generated, then your olefin comes and goes and fit into that vacancy. It goes and interact with metal, and ultimately it would form your metallocyclobutane kind of intermediate, and then it will release the olefin. The key note point over here is metathesis occurs via firstly the dissociation step of PCY3, this bulky group PCY3 that makes it to go away. So this group can, any of the two groups can go away. Once it is being formed, and also the electron density is coming from PCY3 to the metal, that is making a sigma bond. Once the electron density is there onto your metal, it will try to send the electrons from its pi orbitals to the olefin antibonding pi orbitals to make a pi back connection. So because of that, the interaction between the metal and the olefin becomes feasible. Otherwise, it is very difficult. So these are the two important steps that has to be very faster to get the metathesis product. So what we saw, ultimately, we'll be having a new kind of carbene, which can again go back into the reaction, and we will end up having a product olefin. So the different ways to increase the activity of your Grubbs catalyst in olefin metathesis is first to increase the phosphine dissociation. How we can easily take out the phosphine? If we have a bulky group over in our system, that can easily be taken away. Or if we replace the chlorine by iodine group, that also can easily take up your PCY3 group. Okay. So if this is being asked, if you are having, instead of the chloride group, if you are having bromide group or the iodide group, which one is going to have more catalytic activity? The iodide one, of course, because it is increasing the bulkiness. That was regarding the sterics. Now we come to the electronic part where olefin bindings is more important. So that can only be possible if electron density is there onto metal. From where the electron density will come onto the metal, either it is in low oxidation state or it is getting the electron density from the ligands which are attached. So we talked about the more electron donating groups which can connect or donate electron to metal, and therefore metal can then back donate to the olefin, therefore making the bond strong. So these were the two ways with what we can increase our activity. Then we saw if PCY3 in Grubbs first generation is been replaced by the N-heterocyclic carbon. This is your nitrogen-nitrogen imidazole kind of system, where N-heterocyclic carbons are meant to be a very good sigma donors because they are having electrons over here, which can easily be donated to your ruthenium. So why the activity is more with this one? Because of, firstly, it is very bulky, so it can help it to dissociate very easily. Secondly, it is also electronically rich, so it can help the olefin binding very easily. So these are the two important features that we saw from here. And moving ahead, then we saw Herman did a comparison, he was a scientist, and he did a comparison between the two catalysts in case of the cyclooctane ROMP, which is ring opening metathesis polymerization. So what he observed, if you are having a cyclooctane, one double bond, and using the Grubbs catalyst 1 and 2, we will be opening the ring and forming this product. So if you'll see the graph, the percentage yield, the product formation was more when we were using the second generation. The graph instantly goes above and gets saturated. Whereas in case of the Grubbs first, where PCY3 is there, it is slowly increasing and giving us the product. So this compares and gives us a proof of the more activity with our system. Then moving ahead, we talked about the alkene metathesis catalysis, where we again were talking about what are the metals we are taking into picture and how this catalyst is being formed. So this question has been asked in the last assignment also, when we have a WCl6 and dimethyl aluminum chloride. The two chloride would be replaced by your methyls, and in presence of the ethanol, water goes off and it, W gets oxidized. Tungsten gets forms double bond O, And then here becomes an interaction where the hydrogen from CH3 that cleaves and makes a bond with your CH3, since it is going as this one, and therefore pi bond starts forming between your tungsten and CH2. Therefore, the new catalyst for the metathesis. After that, we saw the shock complexes. This is the shock complexes where we have molybdenum as the metal system, and you can see an imide bond coming from your enolate kind of system. So the best part of here is it is having CF3 groups very far from the molybdenum, but it is still there. And it is an electron withdrawing group, which is increasing and helping in having the activity. It is increasing the catalytic activity. Even sterically hindered things can also be easily can also come under catalysis, but the disadvantage with them is that they have poor functional group tolerance if they're having any other functional group in picture. Say for example, carbon monoxide or NH3 or any oxygen related group, so they are prone to get affected by that. Whereas in case of the Grubbs complexes, which is another type of metal carbon, so here they are having a high functional group tolerance. We have already seen that they're easy to be made and they're handling very easily. But disadvantage that we can't do the metathesis of tri and tetra substituted olefins when we are taking a Grubbs catalyst. But both of them, if you see the coordination number, they are easily been said as a low coordinated system because PCY3 goes away and then makes a contact with the olefin. So this was the part 1 of today's session. And then we talked about the part B, which involves So then we talked about the part B where we talked about the cross metathesis. Firstly, to understand the cross metathesis, we should be clear with the our self metathesis. That means self metathesis, if we are having R1 and R2, R1 and R1, they will both combine together to give you the same product that comes under self catalysis. But if we are having a two different olefins over there, we tend to get different products, as we have already seen, easy form as well as homodimers and heterodimers. So then in the market, there was a talk about, there was a need about making soft detergents. And for that, we need to have a range of carbon number from C12 to C18. And it's very difficult to form from any places. So shop shell higher olefin process came into picture where we saw that starting with the ethylene and a catalyst, the nickel catalyst, it goes into the oligomerization, it increases the number, and then after catalyst refining, it will give you the catalyst back. Process continues, and the oligomer which has been formed, it will undergo the distillation chamber. Depending on the number, you know that if the number is less, that would be either gases or liquids. As the number increases, the properties, the solid state and liquid nature of your alkenes or any hydrocarbons that changes. So distillation, with distillation setup, we can get our C12 to C18 alpha olefins, which can be used for the soft detergent speaking. The rest part will go under the isomerization. This isomerization will then lead to the cross metathesis and help us to get the required products. So what we saw that if we are starting with C8 and we did the isomerization and then we have a more than C20, C18, then we ended up having this kind of group after isomerization. And after isomerization, we can easily do the cross metathesis of these two things, and we can ended up having a group of carbon number which is required for the soft detergent. Another example we saw with this one with C4 and C2, C22, and they can help us to get C13. But the main disadvantage which we saw with the cross metathesis was that it can form homodimers and cross metathesis product. Both of them, they are having ENZ mixture. That means we don't know regarding the direction of the groups where they are going to be settled. And to limit this particular, to challenge this thing, if we introduce a Grubbs catalyst, it will form the homodimer that would react with your another olefin to give you a cross metathesis as a major product and would decrease the amount of the other homodimers. So this was all about our live session today, the topics that we have to discuss. If there is any doubt, please unmute yourself or can put a question in the chat box before we will take up the questions from the sign. Okay, so if not, then we can clearly answer the following questions in the assignment for that. If you have understood the today's live session or if you have gone through the lectures, the questions in assignment, they are not very difficult to be answered. So as we said, the correct order of the activity for the following three catalysts. Now, if you will firstly recognize these catalysts, these are the Grubbs catalysts. First thing. Then if you see the substituents where the difference is being made, here is the chlorine group, here is the bromine group, here is the iodine group. Rest of the substituents are same. That means these are the only ones which are going to impact it. And as we have already seen, the activity is higher when we have a bulky group. And among the iodine, chlorine, and bromine, iodine is the more bulky, iodide is the more bulky group, then bromide, then chloride. Therefore, we have the order 3 is greater than 2 is greater than 1, which is the C option. I'll get this particular thing confirmed by, we can just skip this part. The answer given is first one. If we are including the electron density into picture, then the triangle will be first, second, and third. Okay, I'll get it confirmed. We can move to the second question. The products in the following reaction is and or are. So if you'll see here, the Hg acetate has been used, and there we have a imidazole kind of system which is already having a positive charge being balanced by chloride group. So this will take up, acetate group will easily take up your H positive from there, and they can be balanced by having an Hg group, because as soon as the H positive will go away, it would form a lone pair kind of system which can connect with your Hg here, and the charge has to be balanced by putting up the 2+ oxidation over here. So this is your required product. This, since we have discussed in the second live session also, the answer is A. Moving ahead, what is the driving force for the acyclic diene metathesis? If you will go back, we have admit group, acyclic diene metathesis kind of system. So the first step of it is like to eliminate the ethylene over there, not the formation of a higher molecular weight polymer or so on and so forth. So the elimination of ethylene is the driving force for happening of the admin process. Then now we want to know the total number of possible self-metathesis products that can be obtained in the given reaction. So if you are talking about the self-metathesis thing, so here the two molecules will be combining together. So it would ended up having R1, R1. So they can be E and Z form. So the two products plus ethylene, it anyway goes similarly here, R2, give you R2 and ethylene. So generally we ended up having 4 kind of products. We'll not even consider this alkene molecule. We don't know the direction of your R2 group, so that would again give you ENZ form. So therefore, possible products, because ethylene they have already given out. So the ENZ formation of this particular thing, that would give you a 4 number. Now the given example is having dyeing kind of system. So we have, this is not the, this is the only dyeing system which we were talking about, and it comes under your admit process. This is not the self metathesis. Self metathesis requires the same kind of olefin. This is not ring opening because nothing is closed. It's already an open ring, and therefore the option is B. This is not also cross method with single molecule, so intramolecular. So admit involves the intramolecular metathesis. So it is your intramolecular metathesis. Then we have the reactions in which cross metathesis is observed. We have already seen that synthesis is related to the acetylene. We will talk about these examples only. So we didn't talk about the cross metathesis over there. The Shop process is mainly dependent on the cross metathesis, which we just saw today. The reagents that generates the carbene in situ. So CH3, NH2, CH2, CH2, CH2 will not give you anything. Formaldehyde, no. This is the only one where it is having a positive and negative over here. So this CH2 negative only can form a carbon system. Then we have the product of the following reaction. We have been given PC/3 and this PPH3. As we know that the following product at this particular temperature would be nothing but your Grubbs catalyst, first generation catalyst, which is PC/3. So they can easily replace that, because this is also 2 electron donor, this is also 2 electron donor, and they can easily replace by the more stable complex formation. So the answer to your question is this one. Then the formation of the major product in metathesis reaction while using the different olefins was correctly predicted by Katz. This we have discussed in our first live session, where he was the one who could see the different kind of olefins using the metathesis process. For olefin metathesis, the intermediate proposed by Calderon, we have already discussed it so many times. Calderon proposed for cyclobutane kind of intermediate, where this kind of intermediate would be formed and metal would be in interaction. Petit talked about tetramethylene kind of intermediate. Grubbs talked about metallocyclopenta intermediate, and Chauvin was the one who talked about the metal carbon interaction and giving metallocyclobutane kind of intermediate. So if you'll see the options, you should be aware of like who has given which process. So answer A is the right option. So with this, we have discussed the assignment solutions. So if you have any doubt, you can still ask the question. We'll wait for 10 to 15 minutes more. Okay, this group meet, this live session would be ending in another 1 minute. If you have any other doubt, please rejoin the same link. I'll be happy to answer your question.